Well, hello. For hundreds of years, scientists have speculated on the wonders of space travel. Recently, new technological advancements have opened doors for new opportunities that have facilitated research in getting projectiles from Earth to Mars.
Can we make it to Mars?
Our goal is to reach Mars in 365 days with a projectile. To do this, we've decided to use a railgun. Railgun is a weapon used in the US military that uses electromagnetic force in order to launch projectiles. However, the most current railguns only shoot projectiles at a maximum speed of 7 times the speed of sound. In order for us to get to Mars in 1 year and escape Earth's atmosphere at its correct exit velocity, we need to reach about Mach 32, or 32 times the speed of sound.
Currently, it is impossible to shoot a projectile at such high speeds due to technological limitations. Because of this, all of our calculations are based off of theoretical advancements in technology.
Another assumption we must make in our calculations is that both the Earth and Mars have circular orbits, and that they're both on the same level plane. We want our projectile to reach Mars in the shortest distance possible. Therefore, we launch our projectile when Mars is 1 Earth year away from being at the closest location to Earth from the original launch time.
Position 1 is Earth's position at launch. Position 2 is Mars' position at launch time. Position 3 is Mars' position 365 days after launch.
Based on the circumference of Mars' orbit, we can figure out how far away position 2 is away from position 3. 687 days is how long it takes for Mars to orbit the Sun, and the circumference of Mars' orbit is 1.43 times 10 to the 12th meters. We set that proportion equal to 365 days over some distance between position 2 and position 3. We can solve for x and find that x equals 7.6 times 10 to the 11th meters.
Using distance between the Sun and Mars and the Sun and Earth when they're on the same side, we could solve for the average distance between the Earth and Mars. 7.8 times 10 to the 10th meters is this distance, and using dimensional analysis, we can divide by days, hours, minutes, and seconds to solve for the speed it would take to travel from Earth to Mars in 1 year.
The speed that we solved for in the previous problem, however, is the speed that we need to shoot the projectile at if Earth is stationary. However, Earth is moving tangentially to its orbit, and so we need to use vector addition in order to calculate the true speed. Based on Earth's circumference and the time it takes to get around the Sun, we can calculate that Earth is moving at 3.0 times 10 to the 4th meters per second. We can use vector addition and Pythagorean theorem to say that the true velocity that we need to shoot the projectile at is 3.01 times 10 to the 4th meters per second. And we can use the inverse tan function in order to calculate that it should be 85.3 degrees from the negative y-axis.
This force is called the Lorentz force, and it's affected by 3 different factors. First, we have the current. The current depends on our power supply, and as you can see, it flows through the positive terminal, or the positive rod, across the armature, a conductive piece of metal which houses our projectile, and out back through the power supply. This circuit and the magnitude of its current is a factor in determining the force. The next aspect we have is the length of our rods. It's pretty self-explanatory, and right now ours is at 400 meters. We have set ours for 400 meters. Third is the magnitude of the electric field. Now to calculate this requires quite a bit of calculus. So what we've determined is a certain size for the radius of our rods and the distance between our rods that will help us come up with a reasonable B.
In order to get our projectile from Earth to Mars in 1 year, we add our escape velocity to the velocity we need in order to get to Mars in 1 year from outer space. We then can solve for force by saying the kinetic energy equals the work, which is the force over a certain distance, which is going to be the length of our railgun, or 400 meters. The mass that we use in this is a mass derived from the Falcon 9 SpaceX rocket. Once we solve for force, we get that the force equals 5.458 times 10 to the 10 newtons. Now, in order to solve for the current that we need to run through the railgun in order to shoot it at 41,000 meters per second, we set up the equation force equals our permeability constant times the current squared over 2 pi times ln of our distance between the two rails minus the radius of one of the rails over the radius of one of the rails. From there, we can solve for I, and we come up with 3.745 times 10 to the 8 amps.
Because we're going to be traveling at about 30,000 meters per second when we hit Mars' atmosphere, it's going to be pretty damn hard to slow back down. So, instead of trying to tackle this problem, we decided to give you a visual representation of what it may look like.